Have you ever stopped to think about why things move the way they do? I mean, everything from a planet orbiting the sun to a baseball flying through the air. Well, it turns out the universe has a rule book for all of that, a set of core principles. And today, we're going to dive into the 3 foundational laws that literally run the show.
But let's start with something you've probably felt. You step into an elevator, the doors close, and as it starts to go down, you get that weird little lurch in your stomach, right? That floaty feeling like you've magically lost a few pounds? Well, stick around, because by the end of this, you'll understand the exact physics behind that sensation. So who figured all this out? The credit goes to one of the greatest scientific minds ever, Sir Isaac Newton. Now, to be clear, he didn't invent these rules. They're baked into the very fabric of reality. But he was the one who looked at the world, at an apple falling from a tree, at the moon in the sky, and saw the underlying pattern that connected everything. And that date in the middle, 1687, that's the big one. That's when Newton published his masterpiece, the Principia. This one book basically laid out the entire foundation for what we now call classical mechanics. It's the reason we can launch satellites and predict their orbits. It was an absolute game changer for humanity. All right, let's get into law number 1. I like to call it the law of laziness, but its official name is the law of inertia. And honestly, it's pretty simple. Objects just want to keep doing what they're already doing. They're lazy. So here's the deal. If an object is sitting still, it's going to stay sitting still unless something comes along and gives it a push or a pull. Makes sense, right? But the flip side is just as true. If an object is already moving, it's going to keep moving in a perfectly straight line at the exact same speed forever. Unless, of course, some outside force messes with it. Think about a satellite just floating through the dead of space. There's no air, no friction, nothing to slow it down. Once you get it moving, it just coasts. It doesn't need engines firing to keep its speed. It's just following the law of inertia, cruising along on its own. But wait a second. You might be thinking, satellites don't just fly off in a straight line. They orbit the Earth. And you're absolutely right. Why? Because there is an outside force acting on it, the constant invisible pull of Earth's gravity. Gravity is that external force that grabs the satellite and bends its straight-line path into a nice, stable orbit. This leads us perfectly into the second law, which you can think of as the big push. So the first law says you need a force to change an object's motion. The second law tells you exactly how much that motion is going to change. It's the beautiful, simple connection between force, mass, and acceleration. And you already know this intuitively. Come on, imagine you give a basketball a good shove. It goes flying, right? High acceleration. Now imagine you give that exact same shove to an SUV. It pretty much does nothing. Maybe it rocks a little, low acceleration. Same force, but because the SUV has way more mass, it's much harder to get it moving. And this is it. This is the famous equation that wraps it all up. F equals m times a. Force is equal to an object's mass multiplied by its acceleration. It looks so simple, but this little formula is one of the most powerful concepts in all of science. It lets us calculate and predict the motion of almost anything. Okay, quick timeout for a super important point people mix up all the time. Mass versus weight. Your mass is the amount of stuff you're made of. It's the same whether you're here on Earth, on the moon, or floating in space. Your weight, on the other hand, is a force. It's the force of gravity pulling on your mass. So on the moon, where gravity is weaker, you'd weigh a lot less, even though you are still the exact same you. Now, F equals m is amazing, but it works best when the mass of an object stays the same. So what about something like a rocket? As it's flying, it's burning through tons and tons of fuel every second, which means its mass is constantly decreasing. It's getting lighter as it goes. How does that work? Well, this is where Newton's true genius shines. His actual second law was even more profound. He defined force as the rate of change of momentum, and momentum is just mass times velocity. By looking at it this way, what we write as F equals dp over dt, the law can handle everything, including objects that are changing mass, like our rocket. It's the more complete, more fundamental version of the rule. Okay, on to our third and final law. I call this one the cosmic pushback. It's all about a deep, fundamental symmetry in the universe. It tells us that you can never have a lonely, isolated force. Forces always, always come in pairs. Newton put it perfectly. To every action, there is always opposed an equal reaction. Now, this might be the most famous of the 3 laws, but it's probably also the most misunderstood. So here's the secret.
The action and the reaction forces always act on different objects. That's the key. Let's go back to our rocket. The rocket's engine pushes hot gas down. That's the action. The gas, in turn, pushes the rocket up. That's the reaction. See? They don't cancel out because one force is on the gas and the other is on the rocket. It's that reaction force on the rocket that sends it to the stars. All right, we've got our physics toolkit, we understand inertia, we have F equals ma, and we know about action-reaction. So now it's time to go back and solve that initial mystery. Why do you feel lighter in an elevator?
Here's the trick. The sensation of your own weight isn't really you feeling gravity. It's you feeling the floor pushing up on your feet. It's a support force. When the elevator is still, that upward push exactly equals your downward weight, and you feel normal. But when the elevator starts accelerating down, the floor doesn't have to push up on you as hard to keep up. That reduced support force is what your brain interprets as feeling lighter. And this is a scary thought, if the cables snapped, you and the elevator floor would be falling at the same rate. There would be no support force at all. You'd be in free fall, and you'd feel completely weightless.
For centuries, Newton's laws were it. They were the ultimate description of reality, and they work flawlessly for just about everything we experience in our daily lives. But as we started to probe the universe in more extreme ways, we realized there were situations where Newton's rulebook needed a few new chapters.
And this is how science progresses. It's not that Newton was wrong, not at all. His laws are a brilliant, fantastic approximation of reality. But when you get to the really weird stuff, things moving close to the speed of light, the bizarre world of tiny subatomic particles, or the crushing gravity near a black hole, you need a more advanced set of rules, the rules of relativity and quantum mechanics. So there you have it. From the simple act of walking to the grand dance of the cosmos, Newton's 3 laws gave us the language to understand motion. They transformed the universe from a mystery into a puzzle we could actually solve. Which kind of leaves you with a pretty exciting question, doesn't it? What new rules are still out there, just waiting for us to find them? Thanks for joining me.